Hello and welcome back to Mrs. O'Graham's Maths. This is a work solution video walkthrough for one of the D&D resource papers. So first of all, a big thank you to D&D Resources for allowing me to use their materials in this way. There is a link in the video description to their website. If you have not already got a paper copy of their booklets, I strongly recommend that you go and order yourself one. They are excellent practice for the externals and well worth the small cost that's there to buy them, so that you've actually done some practice on paper before watching the walkthrough videos. Okay, so this one is for probability distributions paper 91586, and it's their practice external assessment number 6, the last one in the booklet. Okay, so let's tuck into question 1. We've got some information here about the time spent with the dentist is between 5 and 30 minutes, with the most usual time of 15. Now that should indicate to you a triangle distribution because we've got a minimum, a maximum, and a mode in between. Now the oral hygienist is between 15 and 45 with a mode of 35. We need to identify the appropriate probability distribution model. We'll go with triangle, sketch them on the axes below, and include as much information as we possibly can. Okay, so let's start with the dentist. So if we need to go between 0 on the axis at the bottom here, and the highest number that we'll need on any of this is going to be 45. So if we go in 5s, we should be okay. So 5, 10, 15, 20, 25 is going to be here. 45, 40s, just there, 45. So it's going to go up to 50 on our axis. Okay, so I'll just fill in the rest of those details. Now the dentist has a minimum at 5 and a maximum at 30. So that base is 25. The height for the dentist is 2 over b minus a, and that's on your formula sheet, where b is the maximum, 30, and a is the minimum of 5, so it's 2 over 25. So 2 divided by 25 is going to be 0.08 to help us pop this onto the diagram. Now the dentist triangle will be the taller of the two because it's got the narrower base, so we just need to make sure we can go up to at least 0.08. So if we make this 0.1 and we go up in 0.02s, that will work for us. Oops. Like so. Okay, so the mode time for the dentist was at 15 and it's at 0.8, so just here. And you would draw this with a ruler, of course. Okay, now the, what was it, the hygienist? And make sure you're labeling them. I'm doing these in different colors to show which is which, but if you're just doing this with pencil in the exam, make sure you label which is which. Now the minimum for the hygienist is 15, maximum is 45. Now the height for the hygienist is 2 over 45 minus 15. So 2 divided by 30, 0.067. So we're going to have that height is happening at 35, and we need to go up to 0.067, so roughly here. Okay, now calculate the probability that two patients, one that sees the hygienist and the other the dentist, both take more than 25 minutes. Okay, so if we start with the dentist, the probability that that patient takes more than 25. In fact, just to be clear, let's call it D for dentist instead of the X. We need to have a look at that triangle situation. So here is the 25, and we need the area of this triangle. Okay, now if this height here is 0.08, we've got a big triangle of 0.08, and a base from 15 up to 30 is 15. Then the small triangle at 25 would have a base of 5. That means that the height must be 3 times smaller because the base is 3 times smaller. So if we do 0.08 divided by 3, we get I'm going to put that as a fraction just to keep it keep all of its accuracy. So that's going to be 2 over 75. So it's going to be half times the base, which is 5, times the height, which is 2 over 75. So times it by 5, divide it by 2, and we get 0.0667 or 1/15. Now for the hygienist, for them to take more than 25 minutes, let's take a look at where 25 is on their triangle. So just here, it's going to be 1 minus the probability that they take less than 25 minutes, because that triangle is going to be easier to find, this one just here. Okay, so the big triangle up to the mode has got a base of 20 because it's going from 15 up to 35, and the height of that was I can't remember what it was as a fraction, so let's just go 2 divided by 45 minus 15 again. So as a fraction, that's 1/15. Okay. Now the smaller triangle that happens at 25 has a base of 10, 15 up to 25. So that height will be half as much, so it'll be 1/30th. Okay, so our area now is going to be 1 minus half times the base times the height. So 10 divided by 2 is going to be 1 minus 1/6, so that is equal to 5/6. So now the probability of both of those things is 1/15 times 5 over 6. Which is 1/18, or if we need it in decimals, 0.0556. And then assuming this, so the assumptions that we need to make on this, so this last bit here, identify any assumptions, we've got to assume that those two things are independent, of course. Okay, now we've got, we know that there's 25% chance that somebody visiting the dentist requires a filling. On one morning, a dentist sees 9 patients. And we are going to calculate the probability that at least 4 out of the next 9 require a filling. Okay, now we are looking at a binomial distribution here because we have 9 patients, so 9 trials, and a chance of success is 0.25. So the probability that x is greater than or equal to 4 is at least 4. Now on our calculator we can do up to and including, so let's just reverse that around. It'll be 1 minus the probability that x is less than or equal to 3. So now binomial on our stats menu, cumulative, we need to make sure that that data is reading variables and not from a list. We haven't input a list into our calculator, so we need to enter the variables instead. So x is 3. The number of trials is 9. Probability of success was 0.25. So that's a 0.8343. And taking it away from 1, we've got 0.1657. Then we've got the usual expected question of justify our use of binomial. So it's binomial because, and then we'll run through our FIST acronym. There are a fixed number of patients. The chance of each patient needing a filling is independent of whether other patients need fillings. The chance of needing a filling remains constant at 0.25. And there are 2 outcomes: they need a filling or they don't. Okay, a dentist estimates that only 8% of his patients pay using cash. If the probability of at least one patient paying in cash in a day is 0.75, how many would he have to see in, how many would the dentist need to see in that day? So this is an inverse binomial question to be able to work out the value of n. So we know that x is following a binomial distribution with n being the number of patients and 0.08 is the chance of success, the chance that they pay by cash. He wants the probability that X is of at least one of them, so greater than or equal to 1, has got to be 0.075. Now, if we're doing this inverse stuff to work out n, what we actually need to use is the probability that x equals 0, so that's the reverse of this. So if the at least one using cash is 0.75, then none of them using cash is the opposite. It'd be 0.25. Now, the probability that x equals 0 in a binomial distribution means a failure every single time. So that means our failure rate was 0.92. That's done n times over, so that gets times to the put to the power of n, and that will be equal to 0.025. Now we can just use our equation solver, or you can do logs. So let's go the easy route and use equation solver. Okay, so 0.92 to the power of x is equal to 0.25. I'm just using x instead of n. You can go through your alpha menu, put n in if you want to. I'm just saving a bit of time. I'll know that I'm actually thinking of n rather than x. So n is equal to 16.63, or 17 customers if we want to round it to whole number of customers. Although you probably just be fine with 16.63 in this circumstance. Okay, so especially because it's not a question that asks for at least something, it's saying the probability of at least one patient paying cash is 0.75, rather than saying it being at least 0.75. So you can give the decimal answer here. But if you're thinking in real terms, we would have to round that up to being 17 customers, of course. Okay, on question 2, we've got this detail about the number of visits that were made by patients in a 12-month period, and a probability distribution shown in this table just here. Okay, we want to calculate the mean number of visits made by patients to the dentist in a 12-month period. So to do that, we take the value of x and we multiply it by its probability. Now I'm going to show you actually how to do this as you can pop this into your calculator as a table, and sometimes that can save us a bit of time later on. So we're going to go 0, 1, 2, 3, 4, and 5, and in list number 2 we want to put the probabilities. So 0.15, 0.47, 0.18, 0.09, 0.02, 0.04. And I can see I must have made a mistake because I've got a few too many in column 2. I've missed the 3. So that should have been 3, then 4, then 5. Okay, so now our table in here matches the table that's been given to us, albeit this one is going vertically, whereas that one went horizontally. Okay, now we need to just tell our calculator some settings. So under the calculations menu in F2, we've got the settings under F6, and we want to tell it that our items are in list 1, so that's currently fine. But the frequency of them, it's not one thing per thing in list 1. We want to tell it that the frequency is existing in list 2. So we select list and then 2. Because that is what we have popped into here. We've got the item in 1 and its probability in 2. Okay, now we can go back to the calculation options. We're doing calculations on one variable because we've got one variable and its frequencies. We haven't got 2 variables. Now in there it gives us a bunch of useful things. The first one being the mean. So x bar is equal to 1.15. For this type of question, we call that the expectation of x, but if you wrote x bar or even just wrote down the answer, you'd be totally fine. This is just a simple achieved question. For part 2, we want the expected cost that they pay just for their consultations, and then we'll compare it to the average spent the average that they actually spent and see what the difference is where they spent those extras. Okay, so what we need to do is, instead of replacing the number here with the cost. Instead of having the number there, we'll replace it with the cost. So if on the 0, obviously they didn't come, they wouldn't spend anything on the consultation. Instead of a 1, we'd have 85. Instead of a 2 times 85 for the cost of their visits is going to be 170. So I'm just going to go back to the table, and you can see how this is helping us to save a bit of time now, because I just need to repeat this process but put the values in for how much they are spending on it. And we can actually do the calculation in here if you don't trust your mental arithmetic. So we can do 3 times 85, and it will pop that into the table. 4 times 85, 5 times 85. Okay, now we do the same calculation. We're doing it in one variable, and that top value gives us the expected cost now, because we put cost in as the values in that first list. So the expected cost of consultations without the added extras is $134.30, but they have spent on average $148 per person. So the difference we now need to work out there to answer that question. So 148 minus 134. So an average difference of $13.70 spent on other dental products. For part 3, we need to be able to work out the standard deviation and compare it. So again, I'm going to go back to the table in our calculator and change those back to the 0, 1, 2, 3, 4, 5, so that we can work out the standard deviation now. Now, if you were doing this manually, you would do the expectation of x squared minus the mean squared. So you go through that lengthy process. But if you've got it already set up in your table, then you can just go to your calculations menu on one variable, and we can then go and find what we're looking for. Now, looking over at the list of calculations that are given to us, you just need to be able to recognize which one is standard deviation. So this top one I told you, x bar is mean. We're looking for standard deviation is represented by sigma. So we find this one here with sigma of all the n values. Ignore this n-1 thing, it's not used in the stuff we're doing. So we're finding the sigma value of x for n items that we've input. So here is our standard deviation. Now that is obviously bigger than 0.95, so larger than the standard deviation of y. Now we need to think of a reason why that might be so. So that first dentist has more variation. Now that variation can only really happen at the upper end of this, because you can't go into negative visits to the dentist. So it means that he's got more people that are coming for more visits within a year. Now the dentist is quite expensive for most people, so maybe he is in a wealthier area where people can afford to go more often. Next, we have a Poisson distribution. We've got a mean number of calls as being 4.8, just there. We want to work out the probability that there are more than 12 calls. So x is greater than 12 is going to be 1 minus the probability x is less than or equal to 12. Hop on over to your calculator, stats menu. We'll just exit out of where we were before. We're doing distributions, move along to Poisson, cumulative. Now x is 12, and our mean, we just need to be careful here. I didn't quite pick up on that this is in a 3-hour period, so we do need to multiply up our lambda. So lambda in a 3-hour period will be 4.8 times 3. Now I don't need to exit out of here, I can actually just type that straight into here. Okay, so that probability is now 0.3203. So that'll be 0.6797. Then we have to identify any assumptions that we needed to make to do this. So justifying our use of Poisson distribution. Okay, so I'll do that down here. So Poisson, because, and we run through our RIPS acronym. So the events occur randomly and independent. So those phone calls come in at random during that time and they're independent of each other. The P is for proportional. So those phone calls, the number coming in is proportional to the time interval that we're looking at. And the S, the events occur singly or not simultaneously. You can't get two phone calls in at the same time. Now, just before I write that, I just had a thought. We were asked to identify assumptions rather than justify, so we'll just change this to Poisson, assuming these things. Okay, so I'll just write that last one in. Okay, and then we've got a graph of the number of phone calls in 1 hour periods at the dentist's office. We want to check if the Poisson distribution does actually match. So the first thing I'm going to suggest we do is work out the probabilities of 0 to 9 calls using a Poisson distribution. So I've set up this table. I've done it over on the left to leave enough room for writing about it on the right. Let's just pop out of here. We're going distributions, Poisson. We're going to do it at each point. So starting with 0, and the mean is 4.8 because we're just doing it for a 1 hour period. Okay, so that first one is 0.00823. And we'll go through and then I'll do it for 1. We've got 0.0395, and I'm going to go through and do that for each of these, but I'll just pause it while I do that for the video. So I've got all of those on. Now I'm going to pop a line onto the diagram for each of those so we can easily compare. And again, I'll just pause the video while I write those in. So I've popped all of those values on from the table of values that I created before, and it doesn't look like it's a great fit. Those the expected values from the Poisson don't actually match what happened in this hour of this recording of phone calls that were received within 1 hour periods. So then that leads us to try to think about reasons why it doesn't match and pop some stuff into writing here. So I'll just pause while I do that. So what I've put as a suggestion here is that the model might not fit because we actually don't expect that phone calls do come in randomly for something like this. That when you're in a situation of making appointments, it's more likely that you'll get more calls in the morning as people try to grab appointments or need to make cancellations or whatever. There's other things that you can talk about with this. We've done a very brief one because I'm kind of out of space, but it probably would be good to talk about the fact that the shape of the distribution doesn't match, as well as, you know, the individual values. We sort of talked about it with here, but it's just a very simple statement. You could look at where the mean is sitting, and that the Poisson distribution is probably more like it's looking closer to being symmetrical than the actual distribution is, and show that those are different. So overall, this model is not a good fit for the situation. For question 3, we've got a normal distribution that looks a bit like this, where the mean is, where are we at? 115,000, and the standard deviation is 18,000. We want to work out the probability that the dentist's earning is more than 150,000, given that it is already more than 125,000. So this is the probability that both of these things are true. So more than 125 and more than 150 divided by the condition, so the probability that it is more than 125. So going out to our distributions, we're using normal, cumulative. Now for this first one, more than 150 and more than 125 is going to be satisfied by being more than 150. So we're just looking for being past that 150 line. So our lower limit is 150,000. Remember to put the thousands in now. Our upper limit is something very, very big. Sigma is 18,000. And the mean is 115,000. So that likelihood is 0.0259. And we're dividing it by the probability of being more than 125. So here's our 125 line. We want everything more than that. So same conditions, but our lower limit now is 125,000. Oops, too many. There we go. And that is 0.028, nope, 0.2893. So 0.0259 divided by 0.2893 is equal to 0.0895. And the question asks for that as a percentage. So that is 8.95%. Now we have some data from an online poll that asked the dentists what their salary was, and they had to select the category. We've got the responses from 120 of them in this graph. One of the dentists looking at the graph said that 75% of respondents had a yearly salary between 100,000 and 160. Show that the dentist is incorrect and identify the correct percentage and show the calculation. Okay, so we're looking for 100 up to 160. So 100 is just here, 160 is just here, so we need the amounts in between. We've got 16, 18, 16, 12, nope, sorry, 13, that's 10, and this one is 7. So let's add them all up. That comes to 80. So the correct percentage out of, we had 120 people. So divide it by 120, and then we'd times by 100, we're going to have 66.7%. And just to make sure we've answered the question, not 75% stated by this dentist. Now we need to compare the information that we've been given. So what's happened in this graph from the poll and the details that we were given at the start and how they might be similar or different. So we had at the beginning the mean 115, standard deviation of 18, and we want to compare that to what's actually happening in this graph. To make that comparison a bit easier, I've just pulled that down so we can see it on the same screen here. So we've got the first bit of information was saying it's they're normally distributed with these values, and now this is the picture here. Now, looking at that picture, we can see we have a bit of a skew, whereas a normal distribution we would expect to be symmetrical. So let's start by talking about that. The next is to think about comparison of the mean amount. Now, if we've got that skew, the mean will be pulled slightly to the right of the peak of our data here. So the mean is probably sitting in this category around here, just pulled slightly over, somewhere between the 120 and 130 mark. So that's definitely going to be more than the 115,000 that was given to us from the normal distribution suggested data. We can take a look at the standard deviation as well. So on the normal distribution, we were told that that was 18,000. Now, if it was normally distributed, then we'd have most of our data sitting within 3 standard deviations of the mean, so 3 above and 3 below. So that's a range of 54. So if we went 115 minus 54, we'd expect a lower limit about 61, which that could be true for the graph that we have just here. So if we pop a 61 on here, and then if we do 115 plus 54, that would go up to 169, which doesn't quite match the data. Look, there's 169. So let's talk about that. So there's our differences, and we'll think about the why. The whys are happening on the top end of things. So the differences that we're seeing, the bottom seems to match. The mean is slightly pulled up to the right, and the top categories of salary are overrepresented from what we expected. Now, think about what's happened here. We've got an online survey. People were asked to self-report their salaries, and for that sort of thing, they might be tempted to over-report what it is that they're receiving because of a bit of like pride in how much you earn. So this wouldn't be a very reliable way to get this information. So there's a bit of human nature in there. They were also self-selecting whether they took part in this online survey, didn't have to do it. And so your human nature part of that is that you might only want to do a survey if you feel like you're doing well within that category and want to report on it as well. Okay, part B. We have a uniform distribution where the bus is equally likely to arrive at any time between 3:30 and 3:50. So if we set that up as being time after 3:30, so let's say this is 0 minutes after 3:30, and it could be up to 20 minutes after 3:30. It's a uniform distribution, so equally likely all the way through that. Now, if it's got a base of 20, and the area has to add up to 1 because areas within a distribution make the total probability, then that gives us a height of 1/20th. Now the mean on a normal distribution happens exactly halfway along, so that would be at 10 minutes in. I haven't really drawn that particularly well. Let's see if we can get that a little better. That's a bit closer to a half. So the mean would be 10 minutes into this time would be 3:40 p.m. is when we can expect that bus to arrive. Then the standard deviation, the formula on a uniform distribution is to do the maximum minus the minimum, or B minus A, square it, divide it by 12, and then find the square root of that. So we have the B is 20, A is 0, so we've got 20 over 12 and then square rooted. So we pop that into our calculator and then find the square root of that. And just realized I made a mistake. I forgot the squared. So let's just go back and do that again. So 20 squared divided by 12, and we square root that. So that is equal to 5.77 minutes. Okay, calculate the 90th percentile for the arrival time of the bus. So for this, it means we're trying to say, where is the line? So what's the x value that makes this area here be equal to 90%? Now, because that's a rectangle, that's pretty easy to do. We just find 20% of the length of it. Sorry, 90% of the length of it, which is 20. So that is 18. So the 90th percentile, 90th percentile is 18. Oh, here we go, 18 minutes. and then explain what that means in the context of the question. So the 18 minutes is so Jason can expect to wait up to 18 minutes for his bus 90% of the time. And that's the end of this paper and the end of this booklet. If you found this helpful at all, please do interact with the video in some way, because it helps other people to find it too, whether that's to like, comment, subscribe. I also do like hearing from you guys as well. Yep, just interact if you can, and that helps me and the channel out and other people to find this stuff too. And if you're looking for more help on stats, go to my home channel, or I've got stuff on calculus as well. Check out what's there, and good luck with your exams.